Okay, welcome to the first lesson of mechanics in year 2, which is about something called moments. Okay, you'll learn what a moment is in just a moment. Pun not intended. So I'm going to show you a quick demo, and I want you to think about those 3 questions there at the bottom. So which direction do objects left and right move the balance? So you might want to think here about clockwise and anti-clockwise. That might help you to describe it. What's the angle between the balance and the forces? You're going to see that in a moment. And what's the same? What equates when the balance is level? So what do I mean? Well, let's take a look. So here's a demonstration. We've got some pillars holding up some objects here. Okay. Now, what do those pillars do? They provide a support. Okay, that's why nothing's happening at the moment, because it's like things are just sat on a table. So let's remove that and think of this sort of seesaw that we have, and something like that might happen. Probably not too surprising. There's actually a lot of maths going on here, though, and the maths you're going to learn is going to be able to say, like, when will that be in equilibrium? When will it start to sort of rotate, perhaps on one side? And what's it all about? Well, maybe if we remove some of these objects here and we start with something like this. Notice that if I put the same object on both sides, left and right, and it seems to be the same distance away, it's level. Now, obviously, if I just had one, it would go down on one side, wouldn't it? Assuming that this is sort of like a smooth. But if I take the same thing and I put it, say, much closer, that doesn't really seem to do anything. And let's just give it some time to sort of correct. If I put that 5 kilograms there close to it, it doesn't seem to really do much. In fact, if I do it there, it doesn't seem to do anything. Whereas if I start to sort of move it away, it went a little bit then. It's going even more now. And here, that's when it's level. So if you take the same mass, okay, the word mass is important here. If you take the same mass and you have it the same distance away, you will be in equilibrium. The rod won't rotate. Well, you probably could guess that. But how do I know? How do I know? Let's have a quick look. How do I know that if I take something that's a different mass and I drop it here, how do I know what it will do? So I'm doing a little bit of maths in my head, and you can see there it is in fact level. So I want you to look at the notches of how far away things are on the screen and the numbers, and you will notice something. And what you're noticing there is the essence of this chapter. It's about these forces that rotate a rod. These are called moments, and how we know if they will be in equilibrium or not, when things will tilt and when they won't. So forces, linking back to year 12, the force here is actually just gravity, isn't it? There's nothing else going on. It's just the object existing on Earth. So 10g and 5g, that's all that it is. But this distance, let's call this 2. This is like 2 times 10g. Whereas this is 1, 2, 3, 4 times 5g. And actually, both of those things will be 20g. So what I'm doing there is I'm calculating moments. I'm showing that moments will be the same. So this is the essence of what the chapter is about. And there are loads of examples about moments in real life. I'm just trying to think of an easy example. Well, you could try opening the door. Try opening a door near the hinge, and it's very, very hard work. Whereas if you do it at the end, the moment is bigger. That's what we would say. The moment is bigger. Or another example is if you just like hold a pen, for example, and you push a pen at the top quite close to sort of the pivot, it doesn't move very much. But if you put the same force in and you go down here, okay, it's very, very easy to move the thing. So this is all about moments. That's why all of these statements are true. So we're starting to look at something now called rigid bodies. Rigid bodies, so it means things like seesaws, basically. Seesaws, ladders, beams, rods, things like this. These are all called rigid bodies. So they're different to particles. You mainly dealt with particles in year 12. Yeah, particles, you have forces and so on, but they're they're quite different because what we have to do now is we have to take into account rotation. And we just didn't do that before. We didn't do any rotation with particles. In fact, that was one of the modeling assumptions. If you remember, it was that there was no rotation. Rods, we have to take into account another property, which is rotation. Okay? The chapter looks like this. So we talk about moments in equilibrium. That's sort of 4A, B, and C. Then we talk about variations of this idea. 4C is the essence of the chapter. And then I think this is 4D. We talk about, what if, because you would probably assume that the mass is concentrated in the center of whatever you're dealing with. What if that's not true? We look at that. That's called centers of mass. And then we talk about things called on the point of tilting. So, for example, I'm very, very careful. If I move my hands together, it's a little bit difficult to do. Sometimes it will look like there are supports there, but they don't really do anything. They're just sort of sat under there. You can move them. It's a bit like Jenga. You can move them and they're not really doing anything. This is called on the point of tilting. So let's start with 4A. So definitions, first of all. So a moment. What is a moment? Well, a moment is a sort of a property of a force. It's connected to rotation, about clockwise and anti-clockwise and so on. And a moment is equal to force. So force might be, for example, like maybe weight. That's what we had a second ago. It was the weight, like 5G, something like that, multiplied by perpendicular distance, not distance, perpendicular distance. Okay. It's sort of like the turning effect is how much, it's how much things turn, isn't it? We saw that on the seesaw. So a bin far away has a very, very big turning effect. Whereas if you put like a force maybe very close to something, or you don't use a lot of force, you might have a small moment. So weight was our example, but actually it can be other forces, tension, things like this. Force times perpendicular distance. They must be, they must be perpendicular. Okay, there's no choice. If things are not perpendicular, which we will see later, we will make them perpendicular. Okay, so let's do some quick examples. This is a bit like the seesaw that we just had. So moments are force times perpendicular distance. Well, this is like 70 kg. This is 75 kg. So what do we have here? We have a downwards arrow of 70 G. Don't forget the G. That's the really common mistake. Over here, downwards would also be a mass. So 75, so 75 G. Now, what do we have to do? We're done with those now. We've turned the masses into weights. Now we have this force. We do our force multiplied by perpendicular distance, and that's ready for us. So 70 G, well, we still need to multiply it by 10. So actually, we haven't done that yet. 75 G. So 70 G multiplied by 10 would be 700 G. And remember, G is a number. And over here, the same kind of thing, 75 G, and it's 8 meters away. So it's not in the middle. Okay, this thing's not in the middle. 5,880. So overall, what will happen? You have a force over here doing almost 7,000. And you have a force here doing almost 6,000. Who will win? Well, it's A. A is going to win. A wants the thing to go anti-clockwise, and A is going to win. So this whole thing, try and picture this, try and see the seesaw in your mind. This whole thing is going to go anti-clockwise. Let's do some quick examples. So moment is force multiplied by perpendicular distance. They must be perpendicular to each other. So that's 10 away, that's 20. They are perpendicular. You multiply together. Newton meters. Newton for forces, meter for distance, Newton meters. Direction. Which way does it make the thing want to go? It makes the thing want to go clockwise. Okay, so you must say the direction as well. The number, the units, the direction. This is 20 newtons. And what's the perpendicular distance? Is there one? I mean, it's connected to the particle. This is a trick question. They wouldn't ask you something like this. There's no moment, okay? Because we talked about things being perpendicular to each other. Okay. So these ones should be quite nice. You don't really see these. They don't really ask you that, okay? What about this then? So it's at an angle, but it's not 90 degrees. What shall we do? So the secret is this. Force, well, that is force. That line there is force, multiplied by perpendicular distance. Now that is a distance, but it's not perpendicular. Draw in the perpendicular distance. Well, it's perpendicular because that's why I picked it. So this is 10. This whole line here is 10. I need to find another way of talking about this distance. It's not 5, okay? It will be less than 5. So what I'm going to do is I'm going to sort of sketch that triangle. The trick is to keep the force the same and draw the distance line. That's how you know that you've got the right triangle here, okay? So let's do some SOHCAHTOA. I want to talk about opposite to the angle, and that is opposite the right angle, so that must be O and H. So I can make a sign statement. Sine 60 equals the opposite. The opposite is the one that I want because this is perpendicular. I can use that, and at the moment I don't have that. Opposite over 5. In other words, 5 sine 60 equals the perpendicular distance. I'm going to call it PD, perpendicular distance. Well, what did we say? Multiply the force by the perpendicular distance. So 50 sine 60 is going to be, isn't it? So 50 sine 60 Newton meters and clockwise. Okay, so my advice is to kind of go off to the side, do that little triangle, get the opposite side, and then do it. Let's do another one. It's not perpendicular. Draw the perpendicular line. That's a hypotenuse. That's the opposite. It's the same thing again. So it's also got 2m. It's got some letter I don't know. I just have to use that. So sine 30. Let's try and talk about this line here. Sine 30 equals opposite over hypotenuse, which is 2m. So 2m sine 30. That is the perpendicular distance. Don't forget, perpendicular distance multiplied by force. So 20 m blah, 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 sine 30. Sine 30 is a half, so it's going to say 10, 20, unless that's a typo. I think that might be, oh no, sorry, it's just meters, isn't it? That's silly. Okay, that's just 2, so that's why it's a 20. Okay, so 20 sine 30 Newton meters. Or you could make that 10. That's the same as 10. This one here is a little bit different because it uses cosine. Okay, this one uses cosine instead, but you can do the same thing. And after a while, most of the exam questions, okay, look like that. After a while, you get quicker and quicker answering this question. It's not so bad. So I want you to sort of pause for a moment and have a go at this question here. Now, this is, how are you looking at this? You might be confused about this laminar thing. It basically means we're looking down on it like a piece of paper. Think of it like that, okay? It doesn't really do a lot to this question. The laminar's sort of not that important. So I want you to think about, I want you to think about this force over here. And then I want you to think about this force over here. And then I want you to think about the overall effect of both of them. So pause for a moment and have a go. What would happen here? Okay, so assuming you've had a go, 5 and 2 are already perpendicular. You can just multiply those. It's also going to be a clockwise force, so 10 Newton meters clockwise. What's happening here? Well, you might quickly know now that it should be about sine 50. So 2 sine 50 multiplied by 8. Okay, so it'll be 16 sine 50. If you're not sure about that, you need to go back and look at the previous section if you're not sure where that came from. Okay, draw on the perpendicular, do the SOHCAHTOA triangle, blah, blah, blah. So overall, what's the resultant moment? Well, clockwise, anti-clockwise, anti-clockwise is going to win. So the resultant would be 2.3 Newton meters anti-clockwise. Okay, so you're ready to have a go at exercise 4a. Remember, the moment is force multiplied by perpendicular distance. They are measured in Newton meters. Sometimes marks come from the units. They can be clockwise or anti-clockwise, and the shortcut for most of the time when you are happy with this is often you have to use sine for the included angle.